Today we have a there. He works
in the University of Technology.
On some database theory, complexity theory, that's parameterized complexity, and today we're going to talk about all possible definitions of fluid and variants of that.
Okay, yeah, so let's start. This is the plan. Let's see how far I can get with this. Yeah, I would like to start with a bit of motivation, looking at three closely related problems: homomorphism problem, constraint satisfaction problem, or CSP for short, and Boolean conjunctive query evaluation. And it turns out on the logical level, they are all essentially the same. Yeah, so they all come down to evaluating first order formulas that are constructed only from existential quantification and logical end. Yeah, and it will also we will also see that the structure of these problems is best captured by looking at the hypergraph underlying these problems. So very quickly going through these classical problems, which probably everybody is familiar with. In the homomorphism problem, we are given two structures. Each structure is given by a domain and a couple of relations. And the question is, does there exist a mapping from one domain to the other such that all of the tuples from relations in the structure A are sent to tuples in the structure B? And the constraint satisfaction problem is defined that we are given a set of variables, we're given a domain and a couple of constraints, where each constraint consists of a scope, which is just a couple of variables, and a relation. And again, the goal is to find a mapping from the variables into the domain, so as to send all of the scopes into the corresponding relation. Oh, that was the wrong direction. And I mean, you're all familiar with Boolean conjunctive query evaluation. So here we have a very simple query which asks, does there exist a teacher who has a child in her course? Yeah, and we could, in data log notation, we would write it like this. And again, it comes down to searching for a homomorphism from the variables in the query to the domain elements in the database, such that every tuple, every atom in the query is sent to one of the tuples in the database. And it turns out that all of these problems are NP complete. It's possibly easiest seen for the homomorphism problem, which you can consider as a generalization of three colorability. Yeah? Three colorability asks, given a graph, does it have a homomorphism to the triangle? Yeah? So it's clear that all these problems are NP complete, so we have to do something. Yeah? And to analyze the complexity, to identify favorable cases of these problems, we look at the underlying structure, and that is the structure of the hypergraph. So from now on, I will only talk about conjunctive queries, but of course, everything applies to CSPs and to homomorphism problems. Yeah? So for a conjunctive query, the one that we saw before, here again, the corresponding hypergraph, well, a hypergraph is defined by giving a set of edges and a set of vertices and a set of edges. Yeah? And the vertices of the hypergraph correspond to the variables in the query, and the edges are in one-to-one correspondence to the atoms in the query. So for example, this query corresponds to the edge, which consists of the variables, if you wish, S, R, and C, yeah, and so on. Yeah, and I mean, this hypergraph clearly looks a bit cyclic. And if we slightly modify the query, just asking, is there a teacher such that having a child that is enrolled in some course, not necessarily one taught by the parent, then the corresponding hypergraph would look like this. And clearly this has the shape of something acyclic. Yeah? And formally, acyclic conjunctive queries are those which have a joint tree. A joint tree is a tree where we have a one-to-one correspondence between the atoms in the query and the nodes in the joint tree. Yeah? And in addition, this labeling of the nodes with atoms from the query has to satisfy the so-called connectedness condition. That is, the nodes which contain a certain variable from the query must be connected. So for example, here we have P and S, here we have S and S, here we have, and so on, yeah? And these two nodes share no variables, so they don't even share a variable, yeah? So, but they would be allowed to share variables, but only if these variables are also present all along the path, yeah? And it's a classical result that conjunctive query answering is NP complete, so in case of conjunctive queries, one usually cites this paper by Chandra and Merlin. Might well be the case that for homomorphism or for CSPs, the corresponding result has been proved even earlier. And a classical paper by Yanakakis from VLDB 1981 showed how to efficiently evaluate conjunctive queries. We are talking here about combined complexity or query complexity, yeah, to efficiently evaluate conjunctive queries if they are acyclic. And Gottlob, Leones, Carcello in their Fox paper 1998 showed that this problem even lies in the class log CFL. Without going into details, it means it's a parallelizable, highly parallelizable problem. Yeah. And the idea of the Yanakakis is to perform semi-joins bottom up in the tree, top down in the tree, and finally yet another bottom-up traversal. And these semi-joins have the purpose of eliminating so-called dangling tuples, tuples that do not contribute to the final result. And we get essentially this complexity result for conjunctive query evaluation, where I might possibly have forgotten a log factor. It depends on how efficiently you can do the semi-joins and joins, but it's essentially linear in the size of the input and of the output. Okay, so of course a natural question, hopefully now, from now on, I can show a few results which are new to you. Yeah, so maybe you were not aware of the details. I mean, everybody probably is aware of the fact that acyclicity can be recognized efficiently, but here I would like to work out the algorithm that does this. Yeah, the natural question is, given a conjunctive query, is it acyclic? And if yes, construct a join tree. Yeah, and this can be done in linear time, and this result is due to Graham on the one hand and Yu Soyoglu on the other hand, who published this result independently in 1979. And to honor the authors, this algorithm is called usually called the GYO reduction. Yeah, and it goes as follows. Yeah, so first of all, if an atom shares no variables at all with another atom, then we can delete it. Yeah, and this atom, what does it mean for the construction of the join tree? This atom can either be used as root node of yet another tree, so that we actually construct a joint forest, not a joint tree, or alternatively, you can put this node anywhere in the tree because it can never violate the connectedness condition if it shares no variables with the others. Yeah. More interestingly is the second rule: if an atom R has variables which either only occur in R or which are all covered by yet another atom R prime. Yeah, in this case, we call R prime a witness for the case for this situation. Then we can delete R in our reduction algorithm, and ultimately we will append R as a child to the node labeled with R prime in the join tree. Yeah, and a query is acyclic if this reduction, which can be applied with don't care non-determinism, if this reduction yields the empty set of atoms. Yeah.
Don't you need to also eliminate variables?
No, there are two versions of that. But if I immediately eliminate the atom which only has variables occurring in itself or in some witness, then this is good enough. But you're absolutely right. There's a second variant of the GYO algorithm which aims at eliminating variables and or atoms. Yeah, but this is good enough. Yeah. So let's look at an example. There is a conjunctive query. Has absolutely no meaning. Yeah? It's really just there for the sake of illustrating the algorithm. And below we have a joint tree of this conjunctive query. Yeah? So first of all, we check that there's a one-to-one correspondence between the nodes in the joint tree and the atoms in the query. And then for every variable, we have to check that the variables occur in nodes in the join tree that are connected. Yeah, okay. And so now let's work through the GYO algorithm. Yeah, let's give names to these atoms. Yeah, lowercase r1 through lowercase r5, and we start off with the full set of atoms. We notice that R5 has variables only occurring in R5. So we can either take it and construct a new join tree from it, or we can append it anywhere in the tree. So here I decided to append it anywhere in the tree. Yeah, both is fine. Okay, now in the remaining set, we notice that the atom lowercase r1 only has the variable x3, which occurs in several other atoms. So we can choose the witness by don't care non-determinism. So I have chosen this one as the witness. So I will ultimately append the node with R3 to this node. Yeah. Then R2 has these variables x2, x4, x3. Well, x4 occurs nowhere else. x2, x3, for example, occurs here. It would also occur here. So again, by don't care non-determinism, I choose this one as the witness, and I'm allowed to delete this one later. I will append it as a node to, as a child to this node. And the same with R3 and with R4. Yeah, okay. And since we have managed to delete all of the atoms, the GYO algorithm was successful. We have the answer, yes, it is a cyclic. And as a side result, we also have the full join tree for that. Yeah? And how does Yannakakis algorithm work? Well, first, it works by semi-joins in a bottom-up traverse. So first of all, in the join tree, we would label all of these nodes, which are now labeled by atoms. We would, in addition, annotate them by the corresponding relation from the database. Yeah, and then in the first step, in a bottom-up traversal, we would carry out semi-joins in order to reduce at a given node the tuples to those which have a continuation downward, so to speak. Yeah, and then in the second step, we will do a downward traversal, again semi-joins, in order to further reduce the tuples in a given relation to those which also have a continuation to the rest of the tree. Yeah, and then in a final step, we would actually compute the joins in a bottom-up traversal. Yeah, and the correctness of this algorithm comes exactly from this observation. Yeah, so originally every node in the join tree is annotated by some relation that corresponds to the relation from the database, which corresponds to the atom at this node. And after the bottom-up traversal, after the first bottom-up traversal, we have reduced this relation R at a particular node T in the join tree, so to say, to the join of the entire subtree below, rooted at this tree, but projected to the variables which actually occur in this node. Yeah, so there's never an explosion. Yeah, in the top-down traversal, what we get after the top-down traversal is we actually have annotated the relation that annotates a particular node is exactly the entire join projected to the variables occurring in this node. Yeah, and in the last step, in this second bottom-up traversal, we would in a bottom-up manner compute the joins. Yeah, so what we then have as annotation at each node is the full join of the subtree rooted at this particular node. Yeah. Okay, so acyclicity apparently is a favorable property, but it is very restrictive. Yeah, and so I mean, I think this is a typical way of reasoning in the parameterized complexity community. Yeah? You have in general hard problem, homomorphism, CSP, conjunctive query evaluation, all NP complete. You have a favorable case, yeah, acyclicity, and now you somehow want to introduce a parameter which measures how far are you away from the favorable case. Yeah, and this is done by various notions of widths, yeah, all associated with some sort of decomposition of the conjunctive query, CSP, homomorphism, or decomposition of the hypergraph. Yeah, and here are some desiderata that I mean, Georg Gottlob, in his Gems of Potsdok 2016, he formulated these desiderata, of course, I mean, with a little bit of bias, because then it turns out that only HyperTree which satisfies these desiderata. But I think they're natural. So the first one is absolutely natural. Yeah, we want to generalize acyclicity. The second one, I think, is also natural. We want to be able to recognize that we have a favorable case. Yeah, so it should be, so for a given k, it should be feasible in polynomial time to detect that we have, say, width less than or equal k. Yeah, and finally, of course, we also want that this parameter to be of value. Yeah, that if we have a conjunctive query with a width bounded by some constant, then conjunctive query evaluation should be efficient. Yeah, and so here I would now like to I don't know if it's I mean, for most of you, it's just a reminder. Yeah, these very common width notions, tree widths, HyperTree widths, generalized HyperTree widths, fractional HyperTree widths, all associated with some notion of decomposition, tree decomposition, HyperTree decomposition, and so on. Yeah. So the first type of decomposition we look at is tree decompositions. Yeah. We have a slightly more complex query here. Again, no particular meaning, just for the sake of illustrating techniques. Yeah. The corresponding hypergraph would look like this. And a possible tree decomposition would look like this. Now, what is a tree decomposition? Well, first of all, every variable, sorry, the tree decomposition, first of all, is a tree. And you annotate each of the nodes in the tree by a subset of the variables. Yeah, or if you look at the hypergraph, you would say we annotate the nodes in the tree by a subset of the vertices of the hypergraph. Okay? And they have to satisfy, this labeling has to satisfy two important conditions. So first of all, every atom from the query or every edge from the hypergraph has to be covered by one of these sets. Yeah, and these sets are usually referred to as bags. Yeah, so there must be at least one bag in the tree decomposition that contains all of the variables of this atom, which is the case here. Also for this atom, yeah, or for that atom, yeah, and so on. So you can check that this is a tree decomposition in the sense that every atom is fully covered by at least one of the bags in the tree decomposition.
But the bag may be bigger.
Maybe bigger, yes, yeah. Covered just means subset relationship. It does not mean exact covering, yeah. And then we again have the connectedness condition. Absolutely, yes. And there can be, the condition really is just, there must be at least one node which covers all of the variables occurring in an atom. And this must be the case for every atom. And again, we have the connectedness condition, yeah, that the nodes which contain a certain variable in their bag must be connected, yeah, like X or F is here, so we don't need to check the others, okay? Okay, and then the associated width for decompositions is, for technical reasons, it's the maximum size of the bags, so the maximum cardinality of the bags, -1. Yeah, this -1 is for technical reasons to make sure that if we apply this idea of tree decompositions and tree widths to graphs as a special case of hypergraphs, then trees have tree width 1. Yeah, so this is it's just a technical trick. Yeah, okay. And the tree width of a query of a hypergraph is then the minimum width over all its tree decompositions.
So sorry, Reinhard, if you have a joint tree, its width is not necessarily 1.
Yeah, exactly. Absolutely. And this is one of the reasons why in that Gems of Potsdok 2016, Georg came to the conclusion that tree width is not a good measure because it does not generalize acyclicity. Yeah, if you have unbounded arity and you have one atom with a large number of variables, you need to put all of these variables in a bag. So you have a huge tree width, even though this is an extremely simple query, maybe just a single atom, but unfortunately with big arity. Yeah, so that's why tree width is not really the right measure conjunctive query evaluation, even though it has been studied a lot in the constraint satisfaction community. Yeah. Okay. So, but how can we do better? In order to do better, we look at edge covers. Yeah. So with the 3D composition, I said every bag has to cover. Sorry, every atom of the query has to be covered by some bag. So we covered edges by vertex sets. Yeah. But now we do the other, go the other way around. We want to cover vertex sets by edges. Yeah. And an edge cover of a set of vertices is a set of edges so that they contain all of the vertices in such a vertex set. Yeah, does that make sense? And now we add these edge covers to the 3D composition in order to arrive at a better form of decompositions. And it will turn out this, in the first place, we get generalized HyperTree decompositions. So what we now have is we have 2 labels for each node in the decomposition. We still have the bags, yeah, of the 3D composition. And here I'm using the terminology of Gottlob Leonis Carcello because they invented, so to say, HyperTree decompositions. Yeah. So with the key or chi label, we mean the bags, but then we have a second label. We also have what we refer to as lambda label, the set of edges, the edge cover. Yeah. And if we look at the query from before, at the 3D composition from before, it turns out that this would be a viable generalized HyperTree decomposition. Yeah. Here, just notating the edge label and the vertex label, or edge label and vertex label in one. Yeah. So if I say J of da da da, I mean J is the edge cover of precisely these variables. Or if I say here J, but leaving out some variables, and C is the edge cover of the variables X, Y, C, C prime, and Z. Yeah, okay. So, and how do we measure the width of a generalized HyperTree decomposition? Well, it's the maximum size of the edge covers. Yeah, okay. And again, generalized HyperTree width is the minimum width over all its generalized HyperTree decompositions. Okay. And why is it good to have low generalized HyperTree widths? In principle, it's also good to have low tree widths. Yeah, but it's good because we can transform such a query into an acyclic query by performing these local joins that we have here. Yeah, between the edges. So the edge label corresponds to atoms, and we can join these atoms, and what we then get is a conjunctive query. Okay, in addition, then we also have to add as leaf nodes additional nodes which consist of exactly the atoms here. Yeah, but then we really have a conjunctive, we have an acyclic conjunctive query, and we can apply Yannakakis algorithm. Yeah, and so the complexity. Okay, it's higher than with acyclic conjunctive query because we first of all have to compute these joins of up to k relations for each of the edge labels. But then we have the usual upper bound on the complexity from acyclic conjunctive queries from Yannakakis algorithm. With bounded tree widths, it means that we have, so to say, we have to construct views of up to k plus 1 variables if we have a tree width of width k. So we would actually get something like this as the upper bound. Yeah, again, appending then additional nodes, which each node just consists of a single atom. Yeah, we would again end up with an acyclic conjunctive query equivalent to the original one. Yeah, and we can apply Yannakakis algorithm. Yeah.
Yes. Can you go back to one slide, please? So when you compute the join of the lambda edges, do you project on the variables that occur only in the...
Yes, you have to project to these variables. That's important, you know, because sometimes you would violate the connectedness condition if you have the full relation there. And it was actually 2 years prior to this HyperTree width paper, Chekuri and Rajaraman introduced another notion of decomposition, so-called query decompositions, where they insisted that you have the entire relation there. And Gottlob Leonis Carcello in their HyperTree width paper showed that detecting query width bounded by some constant is NP complete, because they managed to reduce exact covering problem to this one. So it's really important that we can have projections of the original queries, and that's why we would have to, we would have to check by which of the nodes is, for example, this atom covered. Okay, if it's covered, okay, in this case it's easy. But where is, for example, I don't know, maybe this also is used to cover some atom, but it's not the atom itself. So we would just add yet another child node which just has as label this atom, and it cannot violate the connectedness condition. We can be sure there is one node which contains at least all of the variables contained in a particular atom. Just append this atom as a child. Yeah. Now,
I'm just wondering, adding in these projections, does that complicate things in the bag semantic setting?
No.
Okay.
It just makes the relation smaller. Yeah.
Okay.
No. Of course, yeah. In theory, it does not change anything. In practice, it might change things. You possibly cannot use certain indexes anymore. I don't know. But from a purely theoretical point of view, to arrive at this upper bound on the complexity, it has no negative effect. Yeah. Okay. Now,
so,
what about compositions? Yeah.
Can you hear me on the Zoom? Can you hear me on the Zoom? Sorry.
In addition to, I think Remy wants to ask a question, it seems, but I can't hear him.
Yeah.
Maybe you can.
Can you hear me? Or maybe I can type it and then we can get back to it.
Someone reads the question.
Sorry.
Yeah, it's a little longer. I can ask later.
Okay. Okay. So the special condition is the following. Yeah. HyperTree decompositions are a special case of generalized HyperTree decompositions. And from a conversation with Dan, I know he criticized the names, yeah, that the natural thing has this attribute generalized, whereas the slightly unnatural thing is just HyperTree decomposition. Well, that's for historic reasons, because HyperTree decompositions were proposed first, and then there was an attempt to get rid of this additional condition, which actually failed. Yeah, and I will tell you about this failure later. So what is this special condition? It says if at some point we project out a variable, yeah, it is contained in the edge that we use in the edge cover, but it's not contained in the bag. Yeah, we project it out. Then it must not reappear below in the tree. That's the special condition. Yeah, or we could also phrase it differently. If we use an edge in the edge cover, then all of the variables which will appear later on down there in the subtree must be put into the chi level, must be put into the bag. Yeah, and the very purpose of this is to eliminate non-determinism from constructing the bag. Yeah, because in the computation, as we will see, we proceed from the edge labels, because for them we have a bound. Yeah, if we ask, does there exist a HyperTree decomposition of width at most k, we have the bound k. Yeah, we have no bound on the variables if we assume unbounded arity. Yes.
So sorry, just to check that I understand correctly. So for generalized HyperTree decompositions, you can cover bags with edge covers however you want. Query decompositions you have to cover exactly, and HyperTree decompositions without generalized is you can cover, but the extra variables have to not reoccur in the subtree below.
I think if I've understood the question correctly, the answer is yes.
Okay.
Yeah.
So do you really have these three notions?
Yes, we have.
Okay.
Sorry, we started with a query decomposition by Chekuri Rajaman are not mentioned here. Yeah,
you mentioned it
but
earlier,
I just mentioned them because the question was whether we have to exactly cover or we have to take everything. No, we do not have to take everything in generalized HyperTree decompositions and HyperTree decompositions. And for Hyper, we have this additional special condition.
Okay.
So it's a special case of generalized. Yeah. In this case, it turns out that the HyperTree decomposition again has width 2, and the minimum width over all HyperTree decomposition is the HyperTree width. Yeah. And actually, this is not by accident, as I will show you that it's very difficult to construct a conjunctive query or a hypergraph where generalized hypertree widths and hypertree widths differ. Yeah. Okay. Okay. Now let's look at the next. For this, most probably I will not come to the very last part of my talk. So this will probably be the last notion of width and decomposition that I'm introducing. So I introduced generalized hypertree decompositions and of course also hypertree decompositions by saying we add an edge cover. And I defined an edge cover as a subset of the edges. Yeah, we could also define an edge cover by a weight function. We put weights 0 or 1 on each of the edges. Yeah, so the ones that I have in my edge cover get edge 1, the ones I do not have get weight 0. And what does such a edge cover cover? Well, it covers all those vertices where the total weight of the edges that contain this vertex is at least 1. I think very natural. Yeah, okay. And this, of course, then we can drop this integral condition, which was done by Coe and Marx in their soda paper 2006. Yeah, they said, let's look at fractional edge covers. So it's exactly this idea, but now a fractional edge cover may assign a weight in the interval between 0 and 1, a non-negative real value between 0, rational is enough, yeah, between 0 and 1, yeah, and again, what are the vertices covered by such a fractional edge cover? Well, it's those vertices such that the total weight that all of the edges that contain this vertex sums up to at least 1. So it's the same idea. Yeah? We just drop the integrality condition. Okay, and so I mean here I'm revisiting the conjunctive query, the 3D composition from before. And I'm indicating the fractional edge cover by a superscript which says what is the weight that I want to put on an edge. So this is not a very exciting example because in most cases I choose weight 1. The only interesting bag is this one where we essentially have a triangle, and it is known for a triangle you can do better than just taking 2 edges. You can put weight 0.5 on each of the 3 edges, and it turns out with this you have weight 1 on each of the endpoints of the triangle. So the fractional edge cover can actually be, the fractional edge cover number can be smaller than the integral cover number. Yeah. And Coe and Marx even give a very, very contrived example of a class of hypergraphs that has bounded fractional hypertree widths, but unbounded generalized hypertree widths. But it's really, it's an extremely contrived class of hypergraphs. Yeah. Okay.
So I have a question on this. Should I ask you or should I type?
They are all clear, yeah, because I mean, with tree widths versus hypertree widths, okay. Yes. Remy knows the question now.
Sorry? Yeah. Should I speak or should I type?
Yeah. Now I hear you very well.
Oh, okay, good. So in non-fractional hypertree decomposition, you would never put the same atom into 2 different nodes because if it's covered in 1 node, then you don't need the other node to get a lower width. So for fractional decomposition, is it ever possible that you can split the same atom into different nodes just to get a lower width?
No. I mean, you still have the basis of all that is the 3D composition. So first of all, you must have bags assigned to each of the nodes in the decomposition such that every atom is covered by at least one of the bags. And then you think about covering them, the bags. In case of generalized hypertree decomposition, you search for edge cover, integral edge covers. In case of hypertree decomposition, you also search for integral edge covers, but you have to be careful with the special condition. And for fractional edge covers, you search for a fractional edge cover. So it's really the 3D composition at the basis of all that is always the same.
I see. So you will still never have the same atom twice for a lower width. Because if you already cover 1 atom, then you don't really need the other node to cover it again.
Yeah, yes.
To get optimal width.
I mean, you might need part of an atom in order to ensure connectedness. Yeah. So I would not quickly say yes. Yeah, I mean, what you can be sure is that in a tree decomposition, there must be some progress. Yeah, it makes no sense to have two adjacent nodes in the tree which have exactly the same bag. Yeah, I mean, there must be, if you look in top-down direction, there must be some new vertex there in the next node. Otherwise, it makes no sense. Yeah. You can easily get rid of such a node otherwise, yeah. And this means that you have this upper bound. You can be sure that the number of variables in the query gives you an upper bound on the number of nodes in a 3D composition, on the number of nodes in the HyperTree decomposition, and everything. Yeah, you can be sure of that. But other than that, I'm not aware of additional restrictions.
Okay, thank you.
But only with the
does it make sense to think of fractional HyperTree with decomposition versus fractional generalized HyperTree?
That is. So with the fractional HyperTree decompositions, there is no special condition. It's really a generalization of generalized. It's the generalized HyperTree decomposition, if you wish. Yeah. Okay. And that's why we get these inequalities, because generalized HyperTree decomposition are a special case of fractional. So if you minimize over something bigger, you have more minimization potential. Again, HyperTree widths, HyperTree decompositions are a special case of generalized. If you minimize over something bigger, you can get something better. Yeah, and this, I mean, it's trivial. Yeah, that you can that you get this upper bound. Yeah, you would just project out essentially everything. Yeah, from the edges that you use as edge cover. Okay, and so we get these results which tell us that conjunctive query answering becomes tractable if it's done over a class of conjunctive queries that has bounded tree widths, that has bounded HyperTree widths, bounded generalized HyperTree widths, bounded fractional HyperTree widths. After what I've said so far, the results are not entirely trivial, yeah, because they assume, so what I've said so far assumes that you have a decomposition of the desired width. Yeah, but this naturally leads to the next question: how efficiently can we find a decomposition of the desired width? Yeah, and so this is a natural formalization of this question. Yeah, we are given a hypergraph, and we assume the widths that we aim at. We assume the width k to be fixed. Yeah, if we assume that the width k is part of the input, then you have NP completeness immediately for everything. Yeah, so that's why. But I mean, the width should be small. What's the purpose of having width 50? Yeah, then you get an upper bound of n to the power of 50 for your query evaluation. It's worthless. So it is a reasonable assumption that the width is small. Otherwise, it is of no value anyway. Yeah, so we assume the width k to be fixed, and we ask for a given hypergraph, is the tree width, HyperTree width, less than or equal k? And in case of a yes answer, we also want the decomposition that witnesses the yes answer. Yeah, otherwise, what's the purpose of knowing? Yes, in principle, this query could be evaluated efficiently, we just don't know how. Yeah, and the state of affairs is as follows: for tree widths, this has long been known, and I mean, it's not just tractable, it's even fixed parameter linear. Yeah, so you have an exponential term in the width in k, so 2 to the power of some function of k times a polynomial in the size of the query or in the size of the hypergraph. Yeah, which is this fixed parameter linearity is due to Bortländer. For HyperTree widths, Gottlob, Leones, Carcello, in their original POTS paper, where they presented HyperTree decomposition, HyperTree widths, they presented their notion of widths and decompositions alongside a polynomial time algorithm for actually recognizing low HyperTree widths and for constructing a HyperTree decomposition. For generalized HyperTree widths, this was an open problem for quite a while, and then Gottlob, Miklos, and Schwentig got the POTS Best Paper Award 2007 by showing, among other results, by showing that this problem is NP complete even if we fix the k at 3, yeah? And we showed at POTS 2018 that also for fractional hypertree widths, even if you ask, does a given hypergraph have fractional hypertree widths less than or equal to, this problem is NP complete. And as a side result, we also close this small gap here that also for generalized hypertree widths, asking is generalized hypertree widths less than or equal to is an NP complete problem. If you ask for generalized hypertree widths 1, that's asking for acyclicity. This is feasible in linear time. Okay. Okay, so, but where is this essential difference? I think this is also something that I inserted these slides because Dan asked me these days, why this special condition? Yeah, and we see it by at least giving the idea of a decomposition algorithm. Yeah, and suppose we have this hypertree, this hypergraph, and we want to construct a hypertree decomposition or generalized hypertree decomposition. Yeah, the idea actually also applies to fraction hypertree decompositions. Yeah, so but suppose that we decide to put the edges E1 and E8 as our edge cover into the root node of the decomposition. Yeah, and suppose further that we put all of the vertices that these nodes, that these edges contain into the bag. Yeah. So what's the effect of cutting out, of choosing, or actually what's the effect of cutting out these edges from the hypergraph? Well, the effect is that the rest disintegrates into components. Yeah. And this is exactly the idea, the key idea of constructing a hypertree decomposition in top-down direction. Guess an edge cover. By some magic, determine the bag which you actually want to cover, which has to be a subset of the vertices contained in the edge cover. This means that the rest of the hypergraph, which you still have to cover, you still have to cover the other edges. The rest falls into components, and you can treat them separately. You can treat them completely independently as subtrees below this node. Why? They can never violate the connectedness condition because they are disconnected as soon as we cut out the variables occurring here. So any variable that two such components share must be contained here. And so the connectedness condition is satisfied. Yeah. And so this notion of components is crucial here. Yeah. And we define, so suppose we are given a set of vertices, yeah, let's call it U, a set of vertices of the hypergraph. And we call two edges U adjacent if even after cutting out the vertices of U, they are still adjacent, okay? And then U connected is the transitive closure of them. And the U component is a maximal set of edges which are U connected. Does that make sense? I mean, I think here it is very intuitive. Yeah, we see immediately these are components after cutting out the variables from the edges E1 and E8.
What is U here?
It's the bag that we want to cover here. We have to somehow find this bag. This is the crux of, and this is the key difference between generalized hypertree decompositions and hypertree decompositions. I will show you on the next slide that for hypertree decompositions, we have a reasonable way of determining a good bag. For generalized hypertree decomposition, we don't. And this is the source of the NP completeness there. Yeah. Okay. So in the first place, we guess, or we determine, yeah, we guess the edge cover. There are only polynomially many candidates if we have a bound K on the size of the edge covers. Yeah. But the crux is how do we get to the set U, that is the set of vertices, the bag that we want to use in order to actually produce these components. Yeah. And an important observation or lemma that Gottlob Jonas Cacello in their hypertree width paper showed is that if you have a HyperTree decomposition, and the same applies to generalized HyperTree decompositions, and it also applies to fractional HyperTree, it applies to all of these decompositions because of the connectedness condition. Yeah, you can always, and if you have such a decomposition of width k, you can always transform it into another decomposition T prime, which does not have a worse width, but now it has the property that below every node, all of the subtrees rooted below this node cover exactly one of the components that you generate by the bag. Yeah, so if we go back here, we would say that we can be sure that below this node, every subtree, okay, in this case, it's very simple, but every subtree takes care of exactly one component produced by cutting out the vertices from these edges. Yeah, and this can always be achieved. And I think it's very intuitive. So also the proof sketch of this lemma is very simple. Yeah, because suppose that you have both components below here. Yeah, then you can on one hand look at all of so you just take, if there are two components, just take two copies of this subtree and restrict one subtree to the variables from one of the components and the other one to the variables of the other component. Yeah, and you can never violate the connectedness condition because whatever they have in common must go through this gateway. That's the very definition of component. Yeah.
So does this mean that you can start with any two hyperedges?
Yeah. Yes. 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 But of course it can fail. Then you check the next one. So I mean, when I say we guess an edge cover, what I actually mean is in a loop run through all possible edge covers. There can only be polynomially many. Yeah. And success of let's go to the algorithm. Yeah. It's not the full algorithm, but it's at least the idea. The idea is that you have a subroutine which tries to construct a portion of the HyperTree decomposition that covers a certain component. So these edges contained in the component must be covered somewhere in a node of the subtree that you construct here. Yeah. So we are given a component, so to say, the task of this subtree that we want to construct, subtree of the HyperTree decomposition, and we are given the bag, so the chi level at the parent of. So where will we append this subtree to the overall HyperTree decomposition? Yeah, of course, initially the component is the entire set of edges, and the parent has an empty bag. Yeah, because we have no parent for the root. Yeah, that's how we start. And then we do the following. Yeah, we guess the edge cover. The edge cover is a subset of the edge, and you take really you may take all of the edges, not just the edges which still have to be covered, all of the edges from the hypergraph, but of course at most k. And this will be the edge cover at one of the children of the parent. Yeah, we have as input the bag of the parent, and we guess now that the edge cover at the child of this parent. And now we have to determine the bag. Yeah, which vertices do we want to cover? Of course, we can only cover vertices which are contained in the edges. That's clear. But which subset shall we take? So first of all, it's clear this is the gateway between the parent and the component below. So if the parent and the component below share a vertex which cannot be covered, then we can immediately stop. We go on to the next edge cover. This is not a valid edge cover because the connectedness condition is violated here. If the parent has something which the component has, but not the child, this doesn't work. Okay, so this is clear. But then we also have to add, so we have to add all of this which is needed to ensure connectedness. But then we still have a lot of flexibility. Yeah. If we have unbounded arity, these edges can be much bigger than that. Which subset do we take? And now what we do is we, in addition, for a HyperTree decomposition, we take all of the vertices which are covered by the edge cover and which occur below. This is exactly the special condition. Everything that occurs below and which is contained in an edge in the edge cover must be put into the bag. So and that's enough. Yeah, we don't need to put more into it. Why would we? We just have to make sure of connectedness, and we have to make sure of the special condition. Yeah, and then we have the bag, and with this we can compute the bag components, and then we go into the recursion. Yeah, so to sum up, for HyperTree decomposition, we can construct the HyperTree decomposition top-down. At each node, we guess at most k edges. The bag of the node is fully determined, and that's it. Yeah. With generalized HyperTree decompositions, we have a problem here. How to determine the bag? Yeah, there can be exponentially many subsets that we still have to consider if we assume unbounded arity. Yeah, if the edges have unbounded size, it's not clear. And this is exactly the source of the NP completeness. Yeah. So the next two slides, they're just here with one message in mind. That is, it's not easy to find a hypergraph where the generalized HyperTree width is better than the HyperTree width. And in this paper by Adler, Gottlob, and Grohe, they found this hypergraph which has generalized HyperTree width 2, but it violates the special condition and it has actually HyperTree width 3. That's the only message of this. And just to keep in mind, it's not easy to find a hypergraph that has a better generalized HyperTree width than HyperTree width. Okay, and in the same paper, Adler, Gottlob, and Grohe also showed that the worst that you can get is that the HyperTree width is 3 times as big as the generalized hyper. But this is an extremely coarse-grained upper bound, and I will show you statistics of benchmark queries that we investigated, and we never found this. Yeah, namely how to read this query. What we did is so in our POTS 2019 paper we presented our hyperbench, a benchmark for hypergraphs. Yeah, and we computed, as far as our algorithms, our programs could, we computed the HyperTree widths, we computed the generalized HyperTree widths, and we determined several further parameters of these hypergraphs. Yeah, and now the question that we ask ourselves is, I mean, if a hypergraph has HyperTree width 2, then the generalized HyperTree width will also be 2, because it's not. 2 means it's not acyclic, and if it's not acyclic, also generalized HyperTree width needs to be 2. Yeah, so the interesting question is, what happens if we have HyperTree width 3? Would we be able to push it down to 2 if we take generalized HyperTree width? What if we have 4? Would we be able to push it down to 3? What if we have 5? Would we be able, and so on? And it turned out in none of the cases we managed to find a conjunctive query, and also so these are hypergraphs obtained from conjunctive queries and from CSPs. And we did not find a single one where we managed to compute the HyperTree width, say 3, and managed to compute the generalized HyperTree width smaller than that. The timeouts refer to the generalized HyperTree width algorithm that we applied. Yeah, so we had a 1-hour timeout, and if within 1 hour we did not manage to come up with any generalized HyperTree width, we said, okay, yeah, it's probably also a fail. But of course, you could argue, well, maybe if we had spent more time, possibly we would have found a generalized HyperTree width smaller than the HyperTree width. Yeah, but the first cases where we managed to find a better decomposition for a better width for the generalized case was from HyperTree width 6 to generalized HyperTree width 5. Yeah, we didn't find better.
What are the numbers in the parentheses?
Yeah, this was the average time that our generalized HyperTree width algorithm needed in order to give a no answer. Yeah, and if it was not possible, so the average is not that bad, but if it was above 3,600, then we stopped. Yeah, so the average only takes into account the successful cases. Yeah. Okay. But then we should not be contented with the tractable class of the tractable problem of computing HyperTree widths. I think it's also a natural question. And how would we have to restrict the queries or the hypergraphs so that also generalized HyperTree widths can be computed efficiently in polynomial time? Yeah, and the same with fractional HyperTree widths and also with possibly approximations. I mean, I will skip that. I mean, the k to the power of 3 is not accidentally here. That's the best approximation in polynomial time that was that was known, that I think that is still known in a paper by Marx. Yeah, Marx showed an approximation algorithm in polynomial time for fractional hypertree. Okay, yeah, so we want to define reasonable classes, non-trivial classes of hypergraphs that allow for polynomial time recognizability of generalized hypertree-widths and fractional hypertree-widths. Yeah? And the restrictions that we considered was bounded intersection property. Yeah? It's a very natural property, I would say, because it says what is the maximum number of variables that two atoms have in common. And if you think of conjunctive queries, I mean, it's very unnatural to join over 10 variables. Yeah, so bounded intersection seems to be a reasonable, a useful measure. And we also had in our investigation of this hyperbench, we noticed that this is indeed usually low. Yeah. Then bounded multi-intersection means we are a bit more liberal. A constant number of atoms do not share more than a bounded number of variables. Bounded rank means the size of the, so it's essentially arity, yeah? Bounded arity, does this mean? So the rank of a hypergraph is the arity of the predicates of the atoms, yeah? And bounded degree, again, this seems rather natural, but it turns out that we found lots of instances with high degree. So degree means in how many edges does a vertex at most occur. So you would actually, in case of conjunctive query, you would join over the same variable many atoms. And apparently this can happen quite frequently. And let's forget about the VC dimension. There are more interesting things I would like to talk about. It's clear that bounded rank implies bounded intersection property, and this in turn implies bounded multi-intersection property. And bounded degree, of course, also implies bounded multi-intersection property. And what we actually showed is that with all these restrictions, we end up with polynomial time algorithms for recognizing low generalized hypertree widths or low fractional hypertree widths. Yeah, the asterisks just mean that these results were shown in later papers. I just want to illustrate the key idea why bounded intersection helps us to make generalized hypertree widths efficiently recognizable. Yeah, and the idea is that we add a polynomial number of sub-edges of the existing edges to the hypergraph, with the idea that then by choosing these sub-edges, appropriate sub-edges, we can always assume that the bag of a node in the generalized hypertree decomposition contains all of the vertices contained in the edges. Yeah, because if a vertex is, or a variable is missing, a variable from the bag is missing in the a variable from the edge cover is missing in the bag, then just replace one of the edges by an appropriate sub-edge so that all of the vertices of this edge are now indeed present in the bag. Yeah, and what is the idea? Well, suppose that at some node in the hypertree or generalized hypertree decomposition, we use an edge E in the edge cover, but we want to leave out the variable x. Yeah. What we can be sure is that the edge E must be covered somewhere. Let's call the node U star, which covers the edge. It must occur somewhere. Yeah. And now we distinguish two cases. Suppose that the edge E is actually used all along the path between U and U star in the edge cover. Then there is no reason why we should not add the variable x to the bags of all of these nodes. There can be no violation of the connectedness condition. So that's a simple case. Yeah. But what happens if we have on this path between U and U star a node which does not have the edge E in its edge cover? Well, by the connectedness condition, we can be sure that all of the variables present here and here must also be present here. Yeah. So in other words, the bag of U, yeah, intersected with, so the bag that so where we want to leave out x, the bag of u intersected with E must be contained in all of these edges. It must be contained in the edge cover and also in the corresponding bags, of course. Otherwise, we have a violation of the connectedness condition. Okay, but this means if we add, so we know E intersected with E1 is bounded by a constant. E intersected with E2 is bounded by, let's call it I, constant I-like intersection. Yeah, okay. So we know that this intersection can have at most k times I elements, where I is a constant because we have bounded intersection property and k is a constant. Yeah, but then we just add all of the subsets of size at most k times I of all of the existing edges to our hypergraph, and we replace E by the corresponding subedge. That's essentially the idea. Okay. Now the question is, are these realistic properties? And the answer is, at least bounded intersection is realistic. Yeah. So in this same investigation, in the same POTS paper, we had conjunctive queries which were taken from applications, from benchmarks, from and we also have conjunctive queries which were randomly generated. With randomly generated queries, nothing of this is true anymore. But for all of the conjunctive queries that we took from applications, we call them conjunctive queries from applications. So it's from other papers, from benchmarks, and it turns out, I mean, even bounded intersection 5 is a rare phenomenon. Yeah, so most of the time you would join over one variable, or you join over two variables. Yeah, you do not. Maybe in some cases you join over 5. You never join over more than 5 variables. At least in all of the benchmark queries that we had. With CSPs, it might be a bit different, but also bounded intersection seems to be a good measure. Yeah, and this was the basis for us for quite a good generalized HyperTree width program, which exploits, which first of all computes the intersection width, yeah, in the hope that it's small. Usually it's 2, 3, 4, and then add all of these sub-edges and then apply simply this algorithm, which always says take the full set of vertices covered by the edge cover into the bag. Yeah, and it performs quite well.
So Reinhard, if I understand correctly, the technique that you just described, where you exploit the bounding intersection property, what it essentially says is it uses the construction of the generalized HyperTree HyperTree.
Sure, you get but it restricts even further, because you might have a legal HyperTree decomposition which is not forced to put all of the vertices that are covered into the bag. Yeah, because then you would even end up with query decompositions, which because of this restrictedness of forcing you to take the entire set of vertices covered into the bag, you again end up with NP completeness. So it's not exactly this. So of course, what you get are legal HyperTree decompositions, but even with some restriction there.
And the algorithm is the same algorithm.
We then simply apply the HyperTree algorithm to it. Yes, yes. Okay, I don't know. I think how much time do I have? Shall I just paraphrase what I wanted to say? I mean, these are smaller chapters. Yeah, so maybe I go quickly through them. Yeah, so I wanted at least to give an idea of the NP hardness result, and I also wanted to just have a very glimpse beyond fractional HyperTree widths to adaptive widths and to submodular widths. Yeah.
I try to listen to it.
What about everybody here with stamina? Okay, so the NP hardness proof. So we proved in this POTS paper 2018, we proved that the following problem is NP complete. Let's fix K, the width, the desired width, to be equal to 2. And the question, so you're given a hypergraph. The question is, does it have fractional HyperTree widths less than 2? Or the other question is, does the hypergraph have generalized HyperTree widths less than or equal to? Okay. And we provided a reduction which simultaneously proved actually both of these NP hardness results. Yeah, and it's a reduction from 3SAT. So given a 3CNF propositional formula, we have to construct a hypergraph with this property that the formula is satisfiable if and only if the fractional hypertree width of the constructive hypergraph is at most 2, and the same with generalized. Yeah, and the easy part of the proof, of the correctness proof, was in this direction. Yeah, so if we are let's assume that the 3CNF is satisfiable. From this, we have to show that fractional hypertree width and generalized hypertree width is at most 2. Of course, it's enough to show that generalized hypertree width is at most 2 because fractional cannot be bigger. Yeah, and then we just construct the hypertree decomposition that we always had in mind when we did the problem reduction. Yeah, so that's the easy part. The hard part was the other direction, and here in particular, suppose that the fractional hypertree width is at most 2. Show that the formula is satisfiable. Yeah, and in order to make sure that fractional hypertree width 2 is witnessed by some decomposition of a form that we wanted to have, we had to throw in lots of gadgets. Yeah, and I just present 2 of them.
So based on the preparation that you gave us, it means that this hypergraph that you need to construct here has all the bad properties.
Yes, it's huge. It's huge.
It's huge, and the arity is huge.
Yes, yeah, the arity is everything is huge. Yes, yes.
But I mean, interestingly, there's also a separating example for generalized hypertree width and hypertree width, right? Because if the hypertree width were the same as the generalized hypertree width,
then it would be easy to find. Yeah.
So the hypertree width of that thing must be 3, you know?
Yes. Yeah. We didn't think about it. Absolutely. Yeah, fully agree. But you have to get used to our custom that use it. No, it's good fun to throw it.
So it might actually be interesting if you can figure out a graph from your construction that actually, or a hypergraph that has these properties that you did not find in the practical instances.
Okay.
Right?
Yeah, it's a good point. Yeah, we haven't done that. Yeah, but it's a good point. Yeah.
Okay.
Sure. It is a contrived hypergraph. Yes, absolutely. Yeah. So I just present 2 ideas of this hardness proof. Yeah. The first thing is that we constructed gadgets. Yeah. And what is known, this was not our invention, it is known that if you have a click in a graph, then all of the vertices of the click must be in some bag. They must occur together in some bag. So we have such a click, we have yet another click. So we throw in these 3 clicks, and it's clear that there must be such nodes in the 3D composition that have at least these bags. And then we augmented even these. So far we just had the graph, but now we turn it into a hypergraph where we throw in big sets M1 and M2 in addition. So from A1 and B1 now not only, so this hyper edge not only contains A1 and B1, but it contains a big set M1 in addition. And the same here. And there's a little lemma that we had to prove, that then there must be a node in the fractional hypertree decomposition of width 2, where all of these additional elements must jointly occur. Yeah. So here I'm just very roughly sketching the ideas. So I ask you to believe me that this is the case. And now suppose that our instance of 3SAT has n variables. Yeah. Then on the one hand, of course, so we actually produce 2 copies of this gadget, the unprimed and the primed copy. So the unprimed copy has the vertices A1, A2, B1, B2, and so on. It has all of this big set M1 union M2, and this consists of another big set, which we refer to as S. But importantly, it also contains, so to speak, an encoding of the variables from the 3SAT instance. Yes.
Yeah, can I just ask, so these sets M1 and M2, they have to be large, but so their size depends on the input phi, or it's
no, it's polynomially bounded. Yeah.
Okay, but
polynomially bounded in the size of the instance of 3SAT,
So
but it's big.
So your reduction requires hypergraph of unbounded arity.
Yeah, absolutely.
Yeah.
Absolutely. Yeah. Because if we have bounded, okay, no, without addition, but bounded arity would certainly not work. Yeah, and when with bounded arity, bounded tree widths, bounded hypertree widths, bounded tree, it's all the same. Yeah.
Yeah, but it could still be NP
But it
hard
could
to
still be
check,
better. Yes, you're absolutely
okay.
right. Yes. Okay, no, but it's clearly unbounded arity what we have here. Yeah, we have huge edges. You will see on the next slide. Yeah, but importantly, what I want to say here is these big sets that I want to put here. Yeah, the unprimed version contains all of the variables y1 or vertices y1 through yn, and they are used to somehow encode the propositional variables. And the primed version contain the set y1 primed through yn primed, and they somehow encode the negation. Yeah, not x1 through not xn. That's the idea here. Yeah, and then we have to encode somehow all of the clauses. Yeah, suppose we have such a clause. All of the clauses have at most size 3, and each clause is encoded by 3 pairs of big edges. Yeah, and I only say one detail of these edges. Yeah, so on one hand there are sets B1, B2. Will not go into detail. Then we somehow partition the big set S, but for each of the clauses, the partitioning is in such a way that you can only produce all of S if you find matching puzzle pieces. Yeah, and importantly, we have to somehow encode that here X3 occurs positively, and we encode that by cutting out Y3 prime from the primed version of the variables. And the idea is, if at some point we decide to pick X3 as our literal which evaluates to true, this corresponds to choosing these 2 puzzle pieces in order to cover all of S in this case. Yeah, and that means we somehow encode X3 should be set to true by leaving out, because this set Z which we have. So yeah, in total we cover B1, we cover B2, we cover all of S, and we cover a subset of Y and Y prime. And Y3 prime will disappear to encode that we wanted to set X3 to true. Yeah, and then you can already imagine what the second 2 puzzle pieces look like. In order to encode that we have not X5, we leave out Y5. So if we use these 2 puzzle pieces in order to cover all of S, we encode that we wanted to set X5 to false, and the same with X8. Yeah, and then ultimately the intended decomposition looks like this. We have the unprimed version of our gadget H0. We have the primed version. Here, all of the vertices Y without prime occur. Here, all of the primed versions occur, and in between, by the connectedness condition, it is clear that we have a monotonically decreasing subset of the Y variables and the monotonically increasing subset of the Y primed variables. And if the chain is long enough, at some point we have exactly the same subset of Y's and Y primes, and there we read off the satisfying truth assignment. Okay, as I said, it's really just a rough proof sketch. Yeah. Okay, so finally a very brief glimpse beyond, beyond fractional hypertree, where I should actually give the microphone to Dan rather than talking about the submodular widths here. But it will be just 2 slides on submodular widths. But maybe you were not aware of adaptive widths. I don't know. Okay, so at least one new item here. So how do we determine the fractional hypertree widths? And the same with all of these other notions. Yeah, we want to minimize something. Yeah, we want to find the best possible 3D composition such that something is minimal. Yeah, okay. And then we can use this 3D composition this decomposition to produce a cyclic conjunctive query and run the Anakakis algorithm. Yeah, and so we end up with a favorable result with an upper bound on the complexity of query evaluation. Yeah, so I will go extremely quickly through these slides because I think Han actually also used exactly these slides, and I think we both have our slides originally from Dan's invited talk at AMW 2017. You were kind enough to give me this slide. You might not remember, but I do. So what they illustrate is if we want to ask for the existence of 4 cycles in a graph, yeah, then no matter how we try to construct a tree decomposition, we always end up with fractional HyperTree with 2. Yeah, you can't do better than that. Yeah, but the worst case optimal join algorithm would actually work in big O of n to the power of 3 over 2. Yeah, okay, and Grohe and Marx introduced a general framework for defining widths, which they call lower f widths. Yeah, and this lower f is a function from the power set of the vertices, so which assigns every subset of the vertices a non-negative number. Okay, and then the f width of a tree decomposition is you apply this function to all of the bags in the decomposition. Yeah, and you take the maximum. And that's then the lowercase f width of a tree decomposition. And the f width of a hypergraph is just the minimum of the f widths that you can get with all of the tree decompositions. Yeah, and then for tree widths, we see it nicely fits into this framework because the function lowercase f just takes the cardinality of each bag minus 1. Yeah, and generalized hypertree width just takes the integral edge cover number of each bag as the function. And fractional edge cover number just takes the fractional edge, fractional hypertree width just takes the fractional edge cover number of each of the bags. Yeah, hypertree width with the special condition does not fit into this framework. Okay, now Grohe and Marx observe that the dual of covering is independence. Yeah, so that is a set of vertices is independent if the intersection with every edge is less than or equal 1. Okay, and again we can drop the integrality condition here. Yeah, because we can think of that the integral edge integral independent set problem now assigns weights to the vertices. And the total weight of the vertices contained in every edge must be at most 1. And again, we can take the fractional relaxation of that. Yeah. So fractional independent set means we have a function that assigns weights between 0 and 1 to each vertex. And the total weight of the vertices belonging to an edge must be at most 1. That's a fractional edge cover, a fractional independent set, but by duality of linear programs, we know that the fractional edge cover number and the fractional independent set number are the same. Yeah, okay, this is just duality of linear programs. And so, and now comes Marx, who introduced uppercase f width. Yeah, and with uppercase f width, you choose a set of such functions lowercase f. Yeah, okay. So each of the lowercase f is a function that assigns a non-negative number to each subset of the vertices. And uppercase f is a class of such functions. Okay. And then the uppercase f width of a tree decomposition is you take the supremum of which f widths would you choose. Yeah. Okay. And then Marx defined adaptive width as the uppercase f width where f is just the set of all fractional independent sets. Okay. And what he showed then is that the following problem becomes tractable if we restrict the conjunctive queries to the class of conjunctive queries with bounded adaptive widths. Yeah, namely, it's Boolean conjunctive queries with truth tables. And this exactly refers to a discussion that we had, I think it was in Antonina's talk, yeah, where we said, okay, in the database area, it is much more natural to represent the database sparsely. You only indicate those tuples which are present. This problem would choose a dense representation. You have all the possible k tuples, or say, I don't know, alpha, if alpha is the arity, you have all of the possible alpha tuples in your table and you annotate them with true or false. Yeah, then you have a dense representation. Of course, in general, this gives an exponential blowup of the input. Yeah, but if we look at Boolean conjunctive query evaluation from this point of view, the dense representation, I'm almost done. Then it turns out that this problem becomes tractable for the class of Boolean conjunctive queries of bounded adaptive widths. Yeah, and under some, to me, not previously known assumption, not one of the assumptions that we have seen on fine-grained complexity here, there is even an if and only if. Yeah,
that's not simply ETH.
But no, the ETH is what we get for submodular widths. So in this paper by Marx, I looked it up this morning to make sure it's some assumption on two-array constraint satisfaction problems. This again might depend on some ETH. I don't know. Yeah. Okay. But let's just recall what we have. Yeah. The fractional HyperTree width is defined as the minimum over all 3 decompositions, where we then take the maximum over the fractional edge covers that we compute for each of the bags. Yeah. Okay. So this minimum of over this size that we apply to this function psi that we apply to each of the bags is we compute the fractional edge cover number. And by duality, we know that's the same as the fractional independent set number. And so we could also represent this as minimum over all 3 decompositions of the maximum over all nodes in the 3 decomposition, and then take the maximum fractional independent set applied to each of the bags. Yeah. And the crux of the adaptive width is, in a sense, here we want to find a good 3 decomposition, which is good for every fractional independent set. Here we do it the other way around. For every fractional independent set, we want to find a good 3 decomposition, and this gives us more optimization potential. Yeah, and that's why not if we rush through all this, but it should not be too difficult to verify that the adaptive width is therefore less than or equal fractional HyperTree width. Yeah, and not the other way around. Yeah. There are only 3 more slides now to also make this step to the next, and for me the last notion of width, that is submodular width. Yeah, if we recapitulate, what do we have with the adaptive widths and with these fractional independent sets? So the fractional independent sets are non-negative functions, yeah, defined on sets of vertices. Edge dominated is the term which Grohe and Marx used in order to refer to this condition that f applied to any of the edges must be at most 1. Yeah, so otherwise it would not be independent. Yeah, then we have modularity, that is f applied to set x plus f applied to set y is the same as f applied to the union plus f applied to the intersection. Yeah, and we also have the empty set must be assigned number 0. Yeah, monotonicity follows from the rest. And the only relaxation that Marx introduced when he introduced submodular widths was that modularity was replaced by submodularity. Yeah, okay. And then submodular width is the uppercase f width, where f is the set of non-negative monotone edge-dominated submodular functions with this property that the empty set is mapped to 0. Yeah, and he investigated the Boolean. Well, sadly, all of these papers, Marx, Grohe, they never talk about conjunctive queries in the title. Yeah, I mean the famous paper by Grohe where he showed that tractability of conjunctive query evaluation in case of bounded arity, which is fully characterized by bounded tree widths of the core of the query. the paper has the title essentially homomorphism problem and constraint satisfaction problem viewed from the other side, something like this. So conjunctive theories do not show up in the title. Yeah, and also here Marx proved these results for constraint satisfaction. Yeah, but it's the same problem as conjunctive theories. Yeah, so let us characterize a class of Boolean conjunctive queries by the underlying hypergraph. Yeah, and then he showed you get fixed parameter tractable Boolean conjunctive query evaluation exactly for the class of Boolean conjunctive queries whose underlying hypergraph has bounded submodular widths under the ETH. Yeah, okay. And fixed parameter tractability means that you take the size of the query as the parameter. Yeah, so you get some 2 to the power of size of the query times a polynomial. Okay, it's clear that adaptive width is less than or equal submodular width because we restrict submodularity, of course, implies modularity, but not the other way around. Yeah, and Marx also showed that submodular width is less than or equal fractional HyperTree width, and Marx also showed that bounded submodular width is the same as bounded adaptive width. Yeah, but I mean, because if submodular width is, if adaptive width is bounded by some constant, then submodular width is also bounded. It's just this constant to the power of 4. So, to sum up, what have we seen? Yeah, so the relationship between various notions of width, I think, is well understood. Yeah, we have seen the boundaries of tractability of the check problem. Yeah. There has been made progress with computation of HyperTree decompositions, generalized HyperTree decompositions, fractional HyperTree decompositions. There's also quite some work by another group at TU Wien, by Stefan Seider's group. Yeah, they reduced the problem to SMT solving. Yeah, whereas we actually reduced essentially the problem to HyperTree decomposition solving. Yeah. Yeah, and precise characterization of FBD for CQ answering by this famous result by Marx on submodular width, and the precise characterization of p-time CQ answering in case of bounded arities by this paper of Grohe from 2007. Yeah. So but I think there is still work to do in this area. Yeah. So on the one hand, what has not been achieved yet is a precise characterization of p-time conjunctive query answering for unbounded arity. Yeah. Well, further improvements of decomposition algorithms are welcome, and what we are currently working on is trying to integrate decomposition-based query answering into standard, to somehow combine it with standard query answering techniques. Yeah, integrating these decomposition techniques into Spark, for example, currently what we're doing. Okay, and here are lots of references. Thank you. Yeah, the natural question is where to go for lunch, probably. I think. But if there's a less natural question?
Yes, I have a less natural question. So you say that the relationship between those notions is well understood, but I mean, not really, right? Because we're not really good at separating them really well. Like generalized HyperTree width and HyperTree width, we know that there's a factor of 3 at most.
Yeah.
But I mean, it looked like the biggest difference we've ever observed in the wired is like 1.
Yeah, yeah.
Right? Or do we have any we have any bigger differences?
No, in this sense, it's not. When what is well understood is boundedness. Yeah, we know if one notion is of width is bounded, does this mean that another notion of width is also bounded?
Sure.
And we have an approximation of factor 3, if you wish, for generalized HyperTree decomposition simply by going for HyperTree decomposition. But you're absolutely right. It seems as if this is far too coarse-grained. So whenever I give this talk again, it's somehow understood. It's not well understood.
But do we even know if the difference between HyperTree width and generalized HyperTree width is unbounded?
No, it's not. It's always by a factor, generalized and what and
No,
HyperTree.
no, I mean not as a factor, but as just a number. I mean, you take the generalized the HyperTree width, you subtract the generalized HyperTree width. Do you know if the number that we get there is unbounded?
Ah,
I mean, can it be more than 1,000 or?
yeah, I mean the proof given in the paper by Adler, Gottlob Grohe would suggest that you can blow it up. Yeah,
But
that
they
it's,
only care about upper bounds, right? Or
yes.
or do they also separate?
No. They
Okay.
just say it's at most 3 times HyperTree width plus 1. Okay.
Okay.
No, the other way around. 3 times generalized plus 1 gives you an upper bound on the HyperTree width. Yes.
Yeah. Okay.
But they have this methodological example, right?
Yeah, but this one example just showed HyperTree width 3, generalized HyperTree width 2. It's even difficult to find one where they differ. To find a small hypergraph to some extent intelligible and where they differ.
It cannot be blown up.
This example, not. No. I don't. Oh, sorry. Maybe it does. I've never thought about it. Maybe, yeah. Why not? Why not somehow multiply it? Yeah. Sure. Yeah, we certainly can somehow. Yeah, I would say. I see no reason why you can't blow it up. Yeah.
I have a question. So you
showed us
mostly
that there was an equivalence between the existence of a join tree and the elimination order for GYU algorithm. And somehow can we also express like the Yanakakisian algorithm using the elimination order instead of the join tree? And all of these algorithms for bounded HyperTree generalized trees, can we also express them with using elimination orders?
I mean, for tree decompositions, I think there are algorithms which actually do exactly that they decide on a variable elimination order and then try to construct a tree decomposition following this elimination order. I'm not aware of such an approach to computing HyperTree decompositions, but I mean, at least it sounds plausible, yeah. But I mean, I think also, I mean, the top-down algorithm also somehow makes sense, yeah. That we,
Thanks.
yeah.
One last question, maybe.
can you hear me?
Hi, it's great to see this. Very nice. Thank you very much. I mentioned actually this. So the key idea of this generalized HyperTree decomposition is this projections, right? This idea, and of course exploring connectivity, is also what Dan Willard used for his query optimization. I mentioned he started his work in Harvard thesis in 1970 something.
Oh.
It'd be nice to make comparison or relationship. Of course, his interest isn't hybrid. I mean, there was no such word before.
Okay,
He was just saying,
okay.
here is the class of queries, very general, including, of course, all conjunctive queries. And then he has this optimal results for acyclic graphs.
Yeah, it would be nice to continue this discussion offline. Yeah, I mean, I'm not aware of this work. Yeah, I have to admit.
Yeah, very nice. Thank you. More.
Remy has a question. Okay, so Remy is asking, so what about the width of the data?
Sorry?
How about the width of the data? The width of the, I guess.
Okay, no, this is not at all in the scope of this work. Yeah, this is really just about the query. This work says nothing about any properties of the data. Yeah, and of course also the upper bounds. If you have a favorable query, the upper bounds hold independently of any structural assumption on the data. It's really just structural assumptions on the query.
But is there somewhere we can look to learn about techniques? Yeah.
Figure out where the audio is coming from. Can you try again, Remy?
Oh, can you hear me? It's okay. I can take it offline. Yeah.
Very.
Does anyone know how the audio with this works? Or okay, let's try the. Yeah, if you have a. Sorry? Otherwise, there's like back.
Oh, right. Yeah, if you have a burning question, maybe I guess, I'll just use my hand. Okay.
I can take it offline. I don't want to hold people out for lunch. I don't think I can hear you now. So.
Okay, that's a good idea. But now comes Floris. No.
I'm just ready for lunch.
Ah, okay. Okay.
Thanks, Reinhard.
Thank you. Thanks. I'm happy to do a great job. So